Okay, so good morning and good evening, everyone. Thank you for joining Eisner Seminar series. I'm Miho Yamachi. I will be a chair of this session. The Eisner Seminar series was launched in 2010 upon the inception of Eisner. Since then, seminar series has featured the best researchers in the world on carbon neutral energy issues. Today's seminar is also hosted by CNER, the Moonshot Beyond Zero Emission Society and the Research Center for Negative Emission Technologies. Today, we welcome Professor Andrew Gebos from University of Illinois. So now I'd like to invite our director Sophronis, Petros Sophronis, to give our session. Petros, could you message to us?
Thank you very much, Miho. Since today we have an Eisner Seminar, which is one of our most distinguished events in Eisner, I would like to mention that our mission in Eisner is to contribute to Japan's quest, in fact, the world's quest for a sustainable and environmentally friendly society. In Eisner, we carry out fundamental research that is mission-oriented. In other words, our research tries to enable the development of low-carbon, high-efficiency, and low-cost energy systems that will help Japan on its way to carbon neutrality. The Eisner Seminar series that we instituted upon the inception of Eisner 10 years ago serves exactly this vision and mission of Eisner. The series features distinguished members of the academic community, visionary leaders from industry, and active members of government agencies. Today, it is a distinct pleasure, and I would add singular honor, to tell you that this evening in the United States, that today's speakers in this series is Professor Andrew Gewirth, my colleague in the University of Illinois and principal investigator of Eisner. Professor Gewirth will share with us some of his finest accomplishments in the electrochemistry of energy systems. And without further ado, I would like first to ask my colleague and principal investigator, Professor Shigenori Fujikawa, to talk how his great project Moonshot is working in Japan in general and the world at large. And then Professor Miho Yamauchi will introduce our distinguished speaker this evening. Professor Fujikawa, please take it away.
Okay, thank you very much. My name is Shigenori Fujikawa. Actually, I'm a principal investigator of the Eisner, and also I'm served as a director of Research Center of the Negative Emission Technology. Actually, our research center is a kind of sister institute of Eisner. So our research institute is especially focusing on the negative emission and the subsequent chemical conversion of CO2 storage. And also this center is strongly supported by a Japanese government research foundation, so-called Moonshot Research and Development Program. Actually, this research project is focusing on to create or kind of game-changing or innovate technology to solve, especially for global warming issue. And also some of us, including Miho Yamauchi and other Eisner researcher, was involved in this project. So, our project main target is the CO2 capture directly from the air, and also we have to utilize or circulate this CO2 as a carbon source in our society. In such sense, so CO2 conversion is a pretty important issue. And also, of course, we have to do some cutting-edge research. That is why we have a strong collaboration with also Miho Yamauchi and also Professor Paul Kennis. So hopefully, maybe Andrew Gewirth maybe join our project as an international collaborator, and then we can promote very aggressive research, especially for global issues. That is why I'm very happy to co-host this seminar given by the Professor Andrew Gebos, and I'm looking forward to hear your lecture. Thank you very much. Okay, I will give you the microphone to the Miho Yamauchi.
Thank you very much, Director Petros, Sophros, and Dr. Shigenori Fujikawa. So I'd like to briefly introduce today's speaker, Professor Andrew Gebos. He is very, very famous professor about surface science, and he analyzed the surface state by using advanced characterization techniques. And also he received the various awards such as Department of Energy Outstanding Accomplishment Award in Materials Chemistry. He has authored over 280 papers, delivered over 200 invited talks. Recently, he is developing a new strategy to enhance catalytic performance by applying magnetic field. So I'm interested in his new methodology. So the title of his talk is Understanding and Controlling Electrochemistry for Electrolyzers and Batteries. Yeah, if you, okay.
So let's get started. Thank you very much, Professor. All right, let's hit this button. There we go. It is good.
Perfect.
Yeah. Thank you very much, Professor Yamanouchi, for this very nice talk. Thank you, Professor Sophronis, for directing the Institute and indirectly for the invitation. And thank you all for getting up at 9 o'clock in the morning to listen to me. It's the wrong time for a seminar for you, and it's the wrong time for a seminar for me, so we will all suffer together. Okay, so today I'm going to talk about electrochemistry for electrolyzers. We're going to talk about batteries, and we're going to talk about CO2 reduction. So this is work that's been supported by Eisner, thank you very much, by Shell, and by two Department of Energy centers, the Center for Electrical Energy Science, and EFRC, and the Joint Center for Energy Storage Research, so-called Battery Hub. I have a number of excellent students that worked on various of these projects: Stephanie Chen, Tao Huang, Danielle Henkel, Ken Madsen, Maria Phillip, MJ Shin, Lingzi Song, Reixiang Zhang, and then very good collaborators, Paul Kennis, who you know, and Steve Zimmerman, an organic chemist who you don't know, but he is also important. Okay, so I'm going to have two topics. The first topic is have to do with lithium-ion batteries. And as you know, not this Nobel Prize, but the last Nobel Prize was awarded to these three people: John Goodenough, Stan Whittingham, and Kira Yoshino, for the development of the lithium-ion battery. And this now gives the whole field some legitimacy that it didn't actually have before. You may know that the Department of Energy in the space of a decade declared both batteries and fuel cells to be dead projects, and now they regret that decision. Okay, so again, I don't need to tell you all how a battery works. You know that a lithium-ion battery, when it's fully charged, has lithium intercalated into a carbon. That was really the Yoshino contribution. And then when you discharge the battery, the lithium leaves the carbon, goes into the electrolyte, which is typically a carbonate and lithium PF6, and then intercalates into a transition metal oxide. That was sort of the Goodenough contribution, where it changes the oxidation state, counter ion number, and therefore oxidation state of the transition metal. In this case, this is lithium cobalt oxide. All right, and it's that change in redox state that provides the electron that runs the battery. Okay, so when you see something like this, carbon, carbonate, and oxide, you can just look at this and say there are 8 million ways that you could change the battery. And I'll just write a list right here, and you can look at it later if you want. You can do just different anodes, all right? Go to lithium metal, or use different coatings and architectures, lithium alloys or intermetallics. Silicon is popular, germanium, tin, even going to sodium metal. You can use a different cathode. We all know that cobalt is, what do we say, a metal of revolution, or not found in the right country. And so we want to get rid of the cobalt and put in more, let's say, manganese or nickel or both, or use things like nickel cobalt oxide, nickel manganese cobalt type materials, all right, to get better voltage and maybe even better rates. Okay, we can use alloys or conversion materials. And we can even use other lithium chemistries such as organics or sulfur or even oxygen, if you believe that. Finally, you can use different electrolytes. So the dirty secret about this LiPF6 electrolyte, here's something I'm telling you, you have to promise not to tell anybody else. And that is that if you hydrolyze, or let's say you have a battery fire and you spray water on that battery fire, the lithium PF6 will hydrolyze and generate HF. And HF is very, very bad. If it is in a confined space, it could be very bad for everybody. So people are very interested in dumping the PF6 right here and going with something else, using glimes, ethers, various additives, polymers, gels, ionic liquids, and solid electrolytes, about which we'll speak in just a minute. And then finally, you can even think about using different chemistries. So here we have the anode, the cathode, and the electrolyte, and you can even throw up your hands and say, okay, that's it, we're going to use a different chemistry, divalents, such as magnesium, zinc, calcium, even aluminum, even high temperature batteries. Sodium sulfur is an established technology. Liquid antimony has been proposed. I'm not sure what kind of battery that would actually be. Metal halide batteries, the so-called zebra battery, has been around for a little while. And then you could even work with redox flow. So the good thing about batteries is that there's massive amounts of work that can be done. Many, many different ways that you can run the whole thing. The bad thing about batteries is there are many, many, many things to do, and it's a complicated system. What I'm going to tell you about has to do with solid state batteries and solid state electrolytes. And this is a sort of hot topic right now. And it's that way because the organic liquid electrolyte is flammable, and we've all seen those nice pictures of people running through conferences with their PC on fire, you know, holding them out in front of them, that sort of thing. Or maybe you've seen the Shanghai parking garage Tesla fire, for example. These are all exciting videos, definitely going to watch them over and over. But the general problem is that you have an organic electrolyte and a high energy material, this intercalated lithium. If you could dump the electrolyte, get rid of the electrolyte and go solid state, then this would, in concept, provide enhanced safety. But it also would provide a better form factor for the battery. In other words, we can make the battery denser, all right? And that would be good for an automobile, all right? And so I bet you didn't know, or maybe you did know, that you're living in a golden age, in part because of a number of very well-known Japanese researchers. And that is that while early attempts at making high conductivity solid electrolytes didn't come up and match the conductivity, the 10 to the minus 2 Siemens per centimeter conductivity of the present day organic electrolytes, we now have a whole family of solid state electrolytes based on basically thiophosphates, but also some garnets and oxides, but particularly thiophosphates that exhibit conductivities that are as good or better than what you can see in the organic electrolyte. So this is awesome. And so you're saying, great, let's start a company, have a patent, make lots of money. But there's a problem. And the problem is that while the conductivities are high, the thermodynamic stability of these materials is relatively low. So this is the results of a calculation. You can see that while materials like lithium fluoride or lithium chloride exhibit high stabilities, they're also poor conductors. While on the other hand, these thiophosphate and related materials right here are calculated to have thermodynamic stabilities that are not good on either the anodic or cathodic sides. So we wanted to try to understand what the origin of this instability is, and then use that understanding to design a new electrolyte that might have better or more advantageous properties. Okay, so before we go there, one final thing I need to say is this. Here are some ideas about how lithium conductivity occurs in these solid state thiophosphate or germanium sulfide based materials, right? And the concept is that the lithium is conducted in between tetrahedra of germanium sulfide or thiophosphate right here, right? And it's in between these tetrahedra that the lithium goes. Here the lithium is green, here it's green right here. This is a better cartoon. And that's true for any of these materials, which differ in details about how these tetrahedra are organized, but still have these tetrahedra. Okay. So now what we can do is we can make a little cell. So here's the cell, a piece of lithium down here, the solid electrolyte pellet. So you go and you buy the powder, you smash the powder together in your glove box, maybe hot press or something like that. and then you sputter on top of it a small piece of gold right here. And then you do cyclic voltammetry, because why not, right? And what the cyclic voltammetry shows you is that you start out right here at positive potentials and nothing happens. And then as you move to more negative values, what happens is we start forming the lithium gold alloy, and then ultimately we do bulk deposition of lithium. As we come back and we strip the lithium, the alloy, and then go back to supposedly clean working electrode gold. When we look at the impedance right here, now, unfortunately, I started looking at impedance a lot, so it's very easy for me to look at this. The only thing you need to know, this is the very quick primer on impedance. Look at where the thing goes down. See where the semicircle goes down? This is sort of the cell resistance. So what you can see right here is we have a cell resistance in this thiophosphate material that's 10 to the 4 ohms, 10 to the 5 ohms or so, which is actually pretty bad, even when we start. But then as we cycle, you can see it gets worse, and it just gets worse and worse and worse. And even in this one, the lithium germanium thiophosphate right here, you can see it starts out better, gets worse, comes back, it's worse, gets really worse, worse, et cetera, et cetera. So what's the molecular origin of this change in cell impedance right here and this drop in cell conductivity? Because anytime you have these lower conductivities right here, the cell won't work, you can't flow lithium, the cell heats up, and it's like total disaster. So what's the molecular origin? In order to do that, what we're going to do is an in situ Raman experiment. And so here again is our battery, right? Lithium, solid electrolyte, little piece of gold right here, 15 nanometers of gold. And then what we do is we construct a cell around this. We actually constructed the cell first and then, of course, put the construct in there. Here what we have is we make contact with the lithium counter reference right here, and then have a piece of stainless on the top that contacts the gold for current, all right? And then the gold provides the Raman enhancement that makes the whole thing work. Okay, so what do we see? So here we have Raman spectra as we go from relatively positive values where there is no lithium deposition to negative values where we have lithium deposition. And what you can see is when you start, you have this strong peak right here at 426 wave numbers. And that peak is associated with the symmetric stretch of the thiophosphate anion that's part of the solid electrolyte. However, as we get toward the place where we start depositing lithium, you can see that this peak goes away and it's replaced by this one at 385 wave numbers, which is associated with the symmetric stretch of the thiophosphate dimer. All right, and then as we come back, you can see that the dimer band, this one right here, goes away slowly to be slowly replaced by this monomer band at reduced intensity. Now, by doing photo emission, we can find some other ideas about what's present in the battery. And what we now know is this: we have lithium, the monomer, we reduce, we make the dimer, lithium sulfide, which is also not a good conductor, and lithium. Now, recall I told you that conductivity in these solid electrolytes occurred between thiophosphate tetrahedra. And what I'm telling you right now is that one consequence of the reduction is to take those tetrahedra and bring them together to block the channels that the lithium is conducted on. And in fact, the conductivity of the thiophosphate dimer is about 3 orders of magnitude lower than what you see in the monomer. All right, so you're making this dimer right here. So you go like, well, that's really bad. That sort of sucks. What else is going wrong? Well, we can even see other problems in the battery right here. Here I'm going to show the results of some tomography. That is where we take the thiophosphate right here and we put it in a small cell and rotate it around at the synchrotron. So we do a sort of a CAT scan for the solid state material. So the first thing you see is this. One of the problems with pellets is that they always crack. If you have students making pellets, they're always going to come back and tell you that they cracked. So you can see right here, even at time t = 0, you see that? I saw this right here. I said, why did you crack it? They go like, they always crack, right? Because they're brittle ceramic materials. And only if you really press them together, and that does some other things to the conductivity, does this not work. So now let's cycle the battery. And you can see the cracks get worse and worse and worse and worse. And if you're proposing that this is going to be a solid electrolyte right here, you're wrong. You know that you have conductivity problems, and you can see already in the current, that's the black trace right here, this sort of oscillatory behavior, which is indicative of instabilities occurring as dendrites are flowing across the whole thing. Okay, So this is a big problem, right? So many people thought that these cracks were developing because of the formation of dendrites. That is to say, when you deposit lithium, the lithium doesn't grow layer by layer, but rather sort of makes these little spikes called dendrites that come out. The dendrites then in this vision would provide pressure, stress that would cause this cracking to occur. So we wanted to see whether that was true. So one of the nice things about the tomography is you can look at layers, any layer you want. And here we're looking at the top layer, just below the lithium. And you can see as we do the cycling, this fuzz is growing on top of the electrode. You see the fuzz right here, this brighter yellow material in the images right here. And so you can see there's almost nothing here, but here it's growing, 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 growing. We can look at the X-ray density of this fuzz. And what we find is that this fuzz is a density that's consistent with the formation of lithium sulfide. And you can see if you look at the potential dependence of this growth right here, this is the growth of it, the derivative of the volume change. You can see that as we go to negative potentials and deposit, right, we get more growth and then it stops growing sort of, and then more growth, et cetera, right? So the lithium sulfide is bad news because it's expanded relative to the thiophosphate. And when we look more carefully, you can see right here, here's the lithium sulfide forming on the surface, and then it grows, it's expanded relative to the underlying material. So now there is stress in the material, and you get more expansion, and then critical stress happens, and we form a crack. And the crack right here is what we're seeing in the tomography. So this is even worse than dendrites, right? This is showing, see the crack right here? See, we have a little arrow for the crack. So this is even worse than dendrites, because this says that the formation of cracks and the destruction of your solid electrolyte material doesn't have anything to do with how well you made the pellet or how good your students are or anything like that, but rather it just says that this is an intrinsic consequence of having the lithium thiophosphate solid electrolyte near lithium metal, and you can't get rid of it by itself. So solid electrolytes by themselves will not work unless you can find something that's both conductive and stable. And I don't know of anything yet that will do that. There's a couple of reports of people say there might be something, but we can talk about that. All right. So what I need to do is I need to drop the potential before I get to the solid electrolyte. And there are two ways that you can think of to drop the potential that I could think of, right? The first way is to use a semiconductor. Right, so then what we would make is a well-known space charge region right here where the potential would be dropped before you get to the solid electrolyte, right? So here would be the metal up here, here would be the solid electrolyte. The other way you could think of to drop the potential would be using an electrochemical double layer. And here, this is the well-known, this is the Stern model of the electrified interface, the Chapman-Stern model. And here, as you know, we drop the potential very quickly over the first few molecular layers near the electrode surface. So because we had silicon in our evaporator, I go like, yeah, that's what we're going to do. And it turns out that was a really not so smart idea, right? We wrote a paper, but it wasn't a smart idea. And it's not a smart idea. I'll tell you why, right? So here's the construct, lithium right here in a symmetric cell, a little bit of gold to wet, and then some silicon on there, and then the solid electrolyte, and then the same thing on the other side. The problem is that as soon as you start passing lithium, you make the silicon into a lithium silicide intermetallic, and the intermetallic is conductive, and so no longer acts like a semiconductor, it acts like a metal, and then we drop the potential in the same way, and the thiophosphate falls apart, and everyone's unhappy. So no problem. So now my collaborator Jeff Elam at Argonne National Laboratory said, no problem, I can make something guaranteed to be an drop the potential. Here we have an insulator high band gap semiconductor, these lumina or subaluminas right here, and he can make me a 10, and he made me a 10 nanometer layer of this lithium alumina overlayer on the lithium right here. And what we discovered was that even with only 10 nanometers, it was too resistive. And so once we started driving lithium, it was unhappy, and then it cracked, and then the lithium with the thiophosphate was exposed to the lithium metal, and all hell breaks loose, right? So we can even try something else, and that is we can use an ionic liquid. And the problem is that while there are some ionic liquids that are stable against lithium, they exhibit low conductivity, and we end up with dendrite formation. Okay, so none of this is all very good. So now I'm going to pull a rabbit out of a hat, or show you something that you might not expect. And the thing that we thought we would try to work with is something called a solvate, or a solvent in salt electrolyte. Perhaps you've heard of the WISE electrolyte, the water in salt electrolyte. This is now more common. And here's the concept. You know that if you have acetonitrile like this, and you put a piece of lithium metal into the acetonitrile, what will happen is the lithium metal will immediately turn brown, and there'll be gas evolution. And I urge you not to breathe the gas, okay? So now what you can do is you can add an electrolyte. Here we're adding lithium TFSI. And we know that the solvent organizes around the anion, and cation in the electrolyte right here. No problem. Now let's add a large amount of electrolyte. And in certain ones of these, you can form a so-called solvate, or a molecular complex right here, where all of the solvent is bound up on the electrolyte. And so there is no free solvent. And therefore, what I can do, and in fact, what I have done, is take a piece of lithium and put it next to this, and nothing happens. So lithium stays shiny and everyone's happy. Okay, so this is very good. Here, for example, I can start making various symmetric cells. Here we have one with the lithium germanium thiophosphate. And you can see that if you just look at the slope right here, you can say that the conductivity is low, and it becomes more and more resistive, right? Acting more and more like a resistor. On the other hand, if I just paint a little bit of solvate next to the thiophosphate right here, you can see now we get good deposition and stripping. And although it's not perfect, it's much more stable over 100 cycle right here than the one without this solvate. Now, in investigations of this, we can do various things. We can also look at this tomography right here. And when we look at the tomography, what we see is that there is no evidence for the lithium sulfide formation. This surface stays clean all the time, even though, and we get sort of fairly good cycling behavior, even though you can see very clearly that there are cracks forming in the electrolyte, in the solid electrolyte right here, as evidenced by the tomography. So we have sort of a mystery. Why do we end up, what's the origin of this cracking right here? And why isn't the battery actually shorting when you see all these cracks? Because you can see right here that the current and the voltage are tracking each other very nicely. Okay, so why is that? So an answer to this comes from cross-sectional EDX measurements on the solid electrolyte near the surface of the solid electrolyte where it has contacted the solvate, and in the bulk of the material. And we find in the ones that are working the best that there's actual adsorption of the solvate into the somewhat porous solid electrolyte. And so the solid electrolyte is sucking up the solvate, and that's causing the swelling and some of the cracking right here. But because the solvate is stable with respect to lithium, everything's working out quite well. And so now you can see right here that immediately let us know, since it's being absorbed, we said, we don't need the pellet at all. What we can do is just mix the solid electrolyte in with the solvate. We're calling this a SOFILM or a SolveSem, depending upon which student was doing all of this stuff right here. And you can see if we just look at the total cell resistance, you can see when we have the interlayer or this SolveSem in there, everything is staying very low and nice. All right, but when we have nothing, the cell resistance just goes up and up and up and up. And so this might be a way to go. The nice thing about this SolveSem material is that it allows us to do other chemistries. And I'll just show you this one very briefly. Here's a sulfur chemistry. All right, so here's the normal lithium-ion battery where we intercalate lithium into a carbon and then into this cobalt oxide right here. We can replace the lithium, the carbon with lithium metal, and we can replace the cobalt oxide with sulfur. And the reason why you want to use sulfur is because it has a high theoretical capacity, and also there are large amounts of sulfur lying around on the ground waiting for people to take. All right, so my student MJ, who was working on this, took vacation in Vancouver, and she took a photo across from the, if you've been to Vancouver, there's this Stanley Park, you know, it's very nice and all that, but she took a photo across the harbor and she said, look, I saw the sulfur pile, right? So here you can see this right here, large sulfur pile in Vancouver. I had to tell her, I said, that's not the sulfur pile. And the sulfur pile is lying on the ground in Fort McMurray, Alberta. You can actually see this on Google Maps. They're pyramids of sulfur from hydrodesulfurization of tar sand derived oil, right? Lying on the ground, and they will pay you to take this away. Okay, so as I said, the nice thing about using the sulfur is that you can get, in concept, better capacity. And there's nothing new. I didn't invent sulfur batteries. They've been around for a long time. So, you know, and here's the theoretical performance right here, well above 1600 milliamp hours per gram, much better than the intercalation cathodes that we were talking about before. And so when you start, you see you actually get that, but then as you cycle the battery, you see that the capacity goes down and down and down and down, and everyone's unhappy, right? And after a while, never mind. The reasons for this are well understood. You start out with S8 right here and go to lithium sulfide, but in between you get to these soluble polysulfides. And again, it's well known in this kind of battery chemistry right here, the soluble polysulfides leave the cathode, go to the lithium anode, are reduced, shuttle on back, and completely destroy your capacity. So we thought that possibly by using a solid electrolyte, we could prevent these soluble materials from leaving the cathode, doing the shuttle, and thus we would retain capacity. So in fact, we did that. And so you can see here's the solid electrolyte by itself. You can see capacity is relatively low. All right. And now if we add the interlayer right here, you can see we get somewhat better capacity over more cycling. But as I said, we realized that the interlayer was not the way to go, but rather mixing these. And when we mix them, you can see right here, this sort of SolveSem, you can see now we're staying up here in the sort of 900 milliamp hours per gram of lithium sulfide. We're going sort of anodeless right here, or trying to go anodeless. And that is maintained over quite some cycles. Okay, so we think this is sort of a way to go. Here's the general concept. The solid electrolyte by itself doesn't work. The solid electrolyte with the interlayer isn't working so well. The liquid electrolyte has the shuttle effect, but then everything works much better when we have the SolveSem, or dissolved solvate and solid electrolyte. And so we're very keen on this concept, and we think that there are a number of other chemistries, including sulfur, that can be enhanced by all of this. Okay. So all right, so here's the summary of this part right here. We've used this solvate interlayer right here. It has prolonged cycle life and enhanced thermodynamic stability. And I think that the future right here are various kinds of coatings and evolved hybrid electrolytes like this one to enable both sulfur and organic battery chemistries. Okay, so that's part of the talk right here. If anyone wants to ask me a question now, we can, or I think I'll just move on to the next section if that's okay. Okay, all right. So now I'm going to switch gears entirely and talk about CO2 reduction. And so it's been known for some time that you can reduce CO2. The seminal investigator was a professor in Japan named Hori, right? It was been known for some time that you can reduce CO2 to different products depending upon the electrode material that you use. All right, so it's now understood that if you want to make carbon monoxide and some hydrogen, you can do this with a gold or silver electrode. If you want to make formic acid, you can use tin or lead or mercury. But if you want to make more evolved products like ethylene or ethanol, C2 products, you have to use copper, all right? And the problem is that you can see here that rather than doing something simple like a 2-electron reduction, now we're doing 12 electrons, and it's a coupled proton electron transfer. So it's very complicated, all right? So the hydrocarbons are positives because they're high energy density. They might be an alternative fuel or other feedstocks. So, okay, this is a great idea, but what has happened? Well, so first here we have a chart, and I hate charts and talks, and so don't look at this chart. Just the only thing you need to know is that the potentials for this CO2 reduction are actually relatively modest. All right, you can see that for make ethylene, for example, we're right around 0 volts versus RHE, or here methanol or methane. These are relatively modest potentials right here. In fact, what you see is that when you look at much prior work, you see that people are using relatively negative potentials here, minus 0.35 volts, minus 0.5 volts, minus 0.5 volts. And the current densities you're seeing for this are actually very poor. And so if you're really talking about an electrolyzer, we're not talking, excuse me, about a couple of milliamps per square centimeter. We need an amp, right? So we're a factor of 1,000 or 100 too low relative to what we actually need to run a real system. All right, so 1 milliamp, no. 1 amp, yes. Okay, so what we wanted to do is we wanted to see if we could do something to the copper and do something to the cell to make this work better. Okay, so we've done a couple of different things to do this, and I'm just going to go through very quickly. We discovered a new way of electrodepositing catalysts like copper using a nitrogen-containing molecule. Here we're using something called diaminotriazole, DAT, as an inhibitor. And depending upon the various conditions, we can make wire or dot type structures right here. The growth of these occurs via a process called diffusion limited aggregation in the electrolyte. We can do things in addition to the copper. We can make a copper silver, right? And so here we just add a little bit of silver in there, 6%. We can get a 6% silver deposit, relatively dilute. Again, by changing conditions, we get wire or poly structures right here. And by using XFs, we can show that the foreign metal, the silver, is well mixed. So this is well below something we could see in an XRD to do this. If we don't use the inhibitor, the diaminotriazole, then we end up with something being not well mixed. All right, so the XF shows that we have a nice dilute alloy right here. And we can even do this with tin. All right, same thing. We add a little bit of tin to the plating bath. We have to adjust the plating conditions, but we can end up with a nice well-mixed copper tin alloy, again, on a few percent, 6 or 7% tin. Why do we care about all of this? Well, first, let's just look at areas. You can see that by using lead UPD to understand the areas, you can see that the areas of the DAT and the copper silver DAT are almost the same. The copper tin is a little bit lower. And if we just airbrush copper onto our gas diffusion layer, a piece of carbon paper right here, you can see these areas are really, really low. Okay, so now the other part of this puzzle right here is using a flow electrolyzer. And this is an innovation that came out of Paul Kennis's group. The concept is that rather than having a bubbling CO2 into solution or something like that, which would force you to be in a relatively low pH, what you can do is flow the electrolyte through the cell. Here, what will happen is we will reduce right at this triple phase boundary where the red copper catalyst is, and then CO2 is flowed in on the backside, and here we have this gas diffusion electrode, this carbon so-called Tory paper right here that allows the CO2 to flow through to the triple phase boundary. The reduction occurs, and then the products go out to the GC or to the NMR for analysis. All right. On the other side, of course, if we're doing a reduction, we have to be doing an oxidation. And in these experiments, we're oxidizing water to make oxygen. We can, of course, replace the water oxidation with something else like glycerol, and that's something we're working on very intently right now. Okay, so when we do this, you can say we're doing much better in current density land. So here's the total current density. You can see that the copper is sort of okay, 100 milliamp per square centimeter. The copper silver is a little bit better, and the copper tin is even better than that. And when you look at the Faradaic efficiencies, or partial current densities for the different materials, you can see that at the end of the day, we're making nearly 60% Faradaic efficiency for ethylene on the tin, somewhat worse on the silver, and on the pure copper, sort of not as good. And that is corresponding to a better formation of CO at intermediate potentials, and then, not so good for the silver, and then not so, even worse for the bare copper. Okay, so what accounts for the differences in the electrode response with the different alloys? Remember, there's only a few percentage of the silver or the tin in the alloy, and yet you can see that just by adding a few percent tin, I go from basically 20% Faradaic efficiency for ethylene to almost 60% right here, right? So that's a big change. In order to understand that, what we're going to do is in situ Raman spectroscopy. So we built a cell. We have a window on the whole thing, and this window allows us to look at what's going on in the surface while we're flowing electrolyte. So here, what you see is the following. If we're just at the open circuit potential, we see three features in the low energy region right here, 1, 2, and 3, that are associated with the presence of cuprous oxide by native oxidation on the electrode surface. So even though we're in alkaline, we still have cuprous oxide right here. And there are three modes. The lowest energy 415 wave number mode is the phonon process. 534 is the T2G Raman active mode. And 620 is the T1U IR active mode right here. Okay, now this is SERS, so surface enhanced Raman spectroscopy. So you see both the IR and Raman active modes. As we go to more negative potentials in the absence of CO2, what we see is either, sort of stability or decline in the normalized intensity of this oxide peak as we go to more negative potentials. And, this is sort of what you expect. You sort of expect to see this declining here, right? Or something like that, because the oxide is supposed to be reduced. And these are relatively negative potentials. You can look at your Porbet diagram and you see, yeah, the oxide should go away, right? That's your concept. So now, this is relatively normal. There's a strong kinetic inhibition, maybe why it's a little bit more stable right here, but you can see declining. And if we were to wait, it would ultimately go away. Now let's do exactly the same thing, but let's do it on the copper surface while we're reducing CO2. So here we have the flowing CO2. So again, here are our three peaks. But now what happens is, as we start to reduce, two strange things happen. The first thing is you see the growth of these two features, A and B. And these are associated with CO on the electrode surface. This one, B in particular, is the copper carbon stretch of the CO. So many times when you're talking about carbonyls, people know that there is a CO stretch around 1800, 1900 wave numbers or something like that. This is direct a stretch of the CO bound to the copper surface, right here at about 360 wave numbers. All right. Now, the other thing that's interesting is you can see this oxide peak right here, rather than declining, is growing as we start doing the reduction. And that's something that really surprised me, right? So again, this is supposed to go away, but as we do the reduction, the oxide is growing in because there has to be a place for the other oxygen coming from the CO reduction to go, at least transiently, and it goes onto the electrode surface. And so you can see right here, we have a plot of the normalized intensity versus the Faraday efficiency, sorry for the lack of a label right here, for CO production. And you can see that this normalized intensity of the CO peak right here goes up, and then it goes down right here as we start forming ethylene. Okay, so now let's see what happens on the other materials. So here's the copper DAT, the copper that we electrodeposited. This is what I just talked about. Look at the copper silver. So first thing you see is that the oxide peak is not nearly as intense as it is in the copper alone case. And the second thing you see is that this peak B associated with CO on the surface becomes more intense. And so here again, you can see this good correspondence between the Faraday efficiency for CO production. It goes up and then it goes down as you start making ethylene, and the normalized intensity of this peak B, this one associated with CO binding on the surface. So it goes up and then it goes down. Let's look at the copper tin. Here you can see it's even better. Look at the massive amount of CO that we have on the surface and almost no oxide present on the surface, particularly these negative potentials where we're forming ethylene right here. And so the presence of this alloy material has removed the oxide from the copper surface and provides more spaces for CO to bind to the surface, and thus gives us more Faraday efficiency for CO and also later on for ethylene. And so again, so let's see, we saw that, right? So here you can see, we can look at the ratio of the peak B, the CO peak to the oxide, and you can see that this ratio is relatively low in the copper DAT. 45 is the number right here, becomes higher, more CO, less oxide in the copper silver, and becomes very high right here in the copper tin. Now you can see that number is sort of like 2000. And so the concept is this: we go and we make, we have CO2, we reduce on copper, we make CO, and the other oxygen goes to oxidize, at least transiently, the copper surface. And then if we have another element in there, it acts as a getter. It's a better oxophile, removes oxygen from the surface right here, oxidizes this to be slowly reduced later on. And then again, we have more space for CO on the surface, and that gives higher Faraday efficiency for CO and thus for ethylene. Okay, and here's the cartoon. The only thing people will remember is the cartoon right here, that without this, we have space for only a little bit of CO on the surface right here, thus relatively little carbon-carbon coupling, whereas with this getter element in here, the tin or the silver, right, we can make CO have more proximity to each other, get better intensity, and thus more ethylene. Okay, good. So we know that what we need to do is we need to control then the amount of oxide that's on the surface right here. And you can control it in a couple of different ways. You can control it, in this case, by putting in a foreign metal, but you can also control it by changing the pH on the surface, right? Particularly as we go to more alkaline pHs, it should be harder to have the oxide grow on the surface, all right? It will stay more, and the oxide will stay more in solution, all right? And so I'm not going to tell you about the pH measurement, but I'm just going to say right here that what we discovered was that we needed to find a way to put some kind of high pKa material onto the electrode surface. And my student Stephanie was talking to someone in the Steve Zimmerman group. He's an organic chemist who makes polyamines. Don't ask me what he wants to do with them. I think they're drugs. I don't know, but makes these polyamines. And she discovered that what you could do was do the same electrodeposition process we've been talking about before, but rather than using diaminotriazole as the additive, she would use these polyamines right here. What we know is that the polyamine is occluded or brought in to the deposit through the electrodeposition process. So here again, we have the gas diffusion electrode. That's this grid thing right here, all right? And then we can just essentially deposit it straight on the electrode. The structure of this looks just the same as you would have with another deposition additive. We can see the presence of nitrogen on the surface right here. And the interesting thing is, if we look at this one right here, the fully protonated one we're calling P1, you can see that we get very good production of ethylene. That's this green line right here. So here's the CO, this is the blue right here. The blue is at relatively low potentials, and then it goes away to be replaced by ethylene. The nice thing is that since we have this amine right here, we can methylate it, all right? And so if we methylate, what we can do is make different polymers. If we have 35% methylation, we're calling this P2, 65% methylation, we're calling P3, and full methylation, we're calling P4. And you can see, so same polymer, same business, same electrodeposit, same amount of nitrogen on the surface as determined by XPS. But what you see is that in the presence of, sorry, it's small, I really apologize. All right, you can see that in the presence of the P4, we get much less ethylene, that's the green right down here, and much more hydrogen, which is what you expect if you have an, alkylated or carbonaceous surface right here. All right, so in the case of the P1, fully protonated, lots and lots of ethylene, almost no hydrogen, little bit of some other products like ethanol or other things. Here, relatively little ethylene, lots of hydrogen, and some other C1 products like formate or things like that. So simply by methylating, we can go from ethylene to hydrogen, all right? Maybe you want hydrogen, maybe you don't, I don't care, right? All right, that sort of thing. How does this work? Well, what we can do is we can use our Raman to measure the relative amounts of carb and bicarb in the flowing cell to make a little pH meter right here. And I had a section right there. We can talk about that later if you want. And this in situ Raman measurement then allows us to measure directly what the pH is on the surface after calibration. And what this shows you is that in the case of the copper alone, or the P4, which remember was fully methylated right here, we have a pH of about 10. This is because of the formation of carb and bicarb, any leakage of CO2 into the alkaline electrolyte. On the other hand, the P1 right here raises the pH by almost a full pH unit. Okay, and that does that by this, carbamate formation right here that allows us to bring CO2 closer to the surface and then do the reduction, pulling bicarb out of solution, making carbonate, which is then part of the reduction process. Okay, so this is sort of a cool thing. It's cool in many ways. So then my student Stephanie was all excited. She said, I'm going to get the record. I'm going to get the record. And so she built a cell that had a 10 molar KOH in it. That's not something you would do normally. This is highly corrosive. But in the presence of 10 molar KOH, you can see that we have relatively low cell potentials right here, relatively high Faraday efficiencies for ethylene production. I think it was 87% right here. And this is the record. Don't ask me why we want the record, but it's high. Okay, congratulations. Right. And energy efficiencies for ethylene production now are approaching 50%. All right, which is not so bad, right? That's actually pretty good. So the interesting thing about this polymer business, it turns out, is not only that we can do good things with CO2 production, and it's just a polyamine that we tried. You're going like, why a polyamine? Why not a poly something else, right? And of course, we can do anything we want, right? A polycarbonate, a polysulfonate, right? Why not? But also, it turns out that these composite electrodes, I can tell you, work well for other things. For example, we can deposit the polyamine with platinum and make a very efficient oxygen reduction reaction catalyst or a methanol oxidation catalyst for ways that work in completely different ways, or even an ammonia oxidation catalyst. And so we're very, very excited about all of this stuff right here. And I think this is going to be really, really cool as we start figuring it all out. Okay. So here's the conclusion. We have copper and copper alloy electrodes produced via electrodeposition. We get high Faraday efficiencies and current densities for CO2 reductions. When we add oxaphilic materials, tin, silver, to the copper, it helps remove the oxide, increasing the availability of sites for CO, and that gives us more CO and thus more ethylene. Okay. Raman measurements, which I didn't tell you about, showed how we could control the surface pH, or what was controlling the surface pH right here. And this polymer incorporation leads to very active CO2 reduction reaction catalysts. Okay, so that's the future. Extend the alloy and polymer concepts to other catalysis. And with that, I'll stop. Here's my group. This is MJ, who was really responsible for the battery work, as was Maria. And this is Danielle and Stephanie right here, who really were responsible for the CO2 reduction work. Thank you for your attention.
Thank you very much, Professor Gilbert. I was so surprised that you succeeded in the explanation of the very complicated service event based on the exact experimental result. Thank you very much. So now this session is for, open for discussion. If you have comment and a question, please raise your hand by using the function of raise your hand, or directly you can contact me. So first of all, I'd like to ask you for the first topic, lithium-ion battery. I was so impressed that you succeed the electrode having a crack, still showing a very good conductivity. So I'd like to know the more details about the interaction between a solvate and the electrode.
Right. So you're talking about things like this.
Yeah.
So the concept right here is that the solvate, so you see, even when you start, you always end up with cracks in these solid electrolytes. It's very painful, right? It can be done, so you make them crack free. You have to hot press. It's very painful. But as soon as you expose this to the solvate starts going into dissolving, the solid electrolyte goes into there, and that provides stress in grain boundaries and other low energy regions that pushes the solid electrolyte apart. And so you can see the crack form here, and here's another one right here that grows. However, these aren't vacuum. Rather, they're filled with solvate, which is and partially dissolved solid electrolyte, which is a which is a good conductor. So that's why you don't short. And as soon as we saw that, as soon as I saw that, I go, oh my God, we don't need to make the pellet, right? Which is very painful. If you ever made pellets, painful, right? You don't want to do that, right? Rather, all we need to do is take the powder and just mix it with the solvate and make these composite or hybrid electrolyte.
Yeah, very, very simple, but very effective methodology to make the pellet. Electrolyte. Yeah, very nice finding.
Miho, Andrew, can I ask you about this topic?
Yeah.
Sure.
This is Hiroshige. Thank you very much for a nice talk about the electrolyte and CO2 conversion. So regarding these topics, so by introducing the solvate into the solid electrolyte system, you are also introducing the interface between the liquid and in this case, how the interface will work on the lithium-ion conduction. Do you have any idea or evidence?
Yes, we do. So here is some detailed impedance work. So this is the result of impedance. We can look, for example, at by fitting the impedance, which I'm not going to show you right here. We can back out bulk, grain boundary, and interfacial resistance. All right. And what you can see is that the interfacial and grain boundary impedance in the presence of the solvate right here is actually lower than it is in either the bare or interlayer cases. So if you just have the interlayer, you still have a big interface right there. And essentially what you do when you dissolve them or mix them together, it's not really dissolved, it's mixed together, is that you more thoroughly coat the individual particles, and that lowers the interfacial impedance.
Okay, I understand. So you mean that the liquid phase will work to connect the intergranular, interbulk lithium-ion conduction. So grain boundary should not be used no longer for the lithium-ion conduction.
Correct.
Okay, I understand. So what about the interface conductivity? So in your explanation, lithium is still using the bulk as a conducting pathway in the solid. But at the same time, I assume the interface can work at the lithium-ion pathway for the conduction. Do you have any idea to use the interface at the pathway?
Yeah, this is a good question. Where exactly is the lithium-ion being conducted, right? And we don't really know that. Yeah, good question, right? I will tell you that you need to have a lithium-ion conductor in there. So we saw this and I said, oh, maybe we don't even need the, thiophosphate's not a great material. It hydrolyzes easily, it's air unstable, right? So I said, maybe we don't even need to do that. Let's throw alumina in there, right? Or something like that, right? And so we did. In fact, a company gave me a whole bunch of designer aluminas, right? To try all of this stuff or silicas. And the problem is that those just go and park up on the electrodes and block all conductivity. Yeah. So you need to have the lithium-ion conductor. So we assume, based on that one data point, that we're still having conductivity through the superionic solid conductor.
Right. Yeah, I was asking this question because in the case of high temperature materials, sometimes the surface will work at the ion conducting pathway. And so in that case, the hybridization or decrease in the particle size will increase the conductivity. Thank you.
Thank you very much. So we can receive questions from audience. Please raise your hand. Could you?
Okay, so here we have Ming Han.
Yeah. Please.
Hi. Professor Gravis, thank you for a very nice talk. I have one question in copper 10 system. Have you tried other metal using the same mechanism to increase the Faraday efficiency in ethylene?
Yeah, we haven't tried anything but these two right here. I did have someone making zinc for a little while, you know, why not? But then the polymer stuff came along and the zinc didn't seem to be, it was harder to make the electrodeposit work. You could imagine other oxophiles that might work. Bismuth would be one that immediately pops to my mind, for example, right? Or lead would be another one, right? You can imagine other oxophiles that might work. And the other thing we haven't optimized is the amount, right? We sort of just got to about 6 or 7, you know, atom percent in this electrodeposition thing. But is that the right number, right? Should it be 4%? Should it be 10%? You know, we don't know. So it's a good question.
How about the durability or stability?
Yes. So this is anybody who talks about copper, you know, anytime you ask that question, they all say, you know, nice day, isn't it? Right? And turn around and walk away. So there's always a problem with durability in the copper systems. And that, so we can run these electrolyzers. I think this one, you know, this, if I show you the Kenneth thing or sell you some of these cells right here, this is the Raman cell, right? We can run these electrolyzers for 8 hours, no problem. All right. If we run them for 8 days, there's a definite problem. Okay. And the problems are twofold. First, there's usually precipitation of carbonates onto the electrode, the nature of which depends upon the binder that we use, if we're using a binder, and also the separator or the you know, ion conductor that we're using right here. And then the other thing is the copper starts being unhappy. And the reason the copper is unhappy, or we start getting more hydrogen is out of the copper. And the reason that starts being unhappy is because there's this delicate interplay between oxide and bare copper. And if we start getting rid of all the oxide or depositing, you know, carbonaceous products down there, then it starts acting like a hydrogen cell and it's all over. So 8 hours, okay. 8 days, not okay. Right.
So one last question. The composition dips, the distribution of the 10 is most of the 10 just stay in the near surface, right? So the inner part, there's no 10 or just a few parts of a 10, trace of 10.
No. So, all right. So 2 things. First thing is that in the as prepared electrode, all right, we've shown by XAFs, I didn't show you that XAFs data, but we've shown by XAFs that the tin is well mixed. That is to say that the tin only sees copper and the copper only sees copper. Right, by XAFs. So it's well mixed all the way through. Now, is there a migration of this foreign metal? And that's common, for example, in ORR catalysts, right? Is there migration of this metal while we're doing the electrocatalysis? And there we don't know. But it wouldn't surprise me if there was some.
So maybe it will happen the erroring during the reaction.
Yep.
Okay. Hi. Thank you. Hi. Thank you very much. Yes.
Other comment and questions? Yeah, please. Sorry.
So can I ask you one more question about your CO2 conversion? So what you showed today is the electrochemical conversion of CO2. And in this case, we can do the same thing by separating the process into water electrolysis plus simple catalytic process, gas catalyst catalytic process.
You're talking about Fischer-Tropsch.
Yeah. For example, we can do at the first step we can electrolyze water to produce hydrogen, and the mixture of hydrogen and CO2 will be supplied to some catalysis, solid catalysis, and
usually it's water and it's hydrogen and CO.
Yeah.
that goes to Fischer-Tropsch. So
doing
two electrons on, let's say, gold or silver, right? And then taking hydrogen plus CO and doing, water gas shift, right? To make other products is certainly a way to go. All right. And so then it comes down to a question of what do you want to do, right? Do you want to have an integrated system where you're making ethylene right away? Or do you want to have a system with, an electrolyzer and then another reactor? Right.
Yeah.
And
so
that's,
in fact, go ahead. Go on. Yeah. So in my opinion, so I have never seen the direct ethane formation from CO2 by action, and it is the benefit to you to use the electrochemistry or electrochemical system. So what is the essence that electrochemistry only do the ethane formation in one step from CO2?
So you know that what you need to do to make ethylene is that you need to do carbon-carbon coupling, right? And then proton transfer. Right, to do all of that stuff. So that means you have to have the two carbons fixed next to each other on the electrode surface, and you have to have other protons coming around from the, water, as a consequence of the water oxidation going on the other side. Right?
Yes.
Right.
But what you're doing is not the oxygen removal, but the addition of proton or addition of hydrogen to the reaction phase. Right?
And also oxygen removal.
Oxygen, how? Because you are using alkaline.
Right, correct.
Exactly. I understand.
Yep. Yeah, no, an acid, of course, doesn't work.
Right, exactly. I understand.
Yeah.
So what you're doing is to remove oxygen from the CO2 by using OH minus ion conduction through the electrolyte.
Yep.
So in that case, you are shifting the equilibrium of by removing the oxygen from the reaction side, the reaction zone.
That's correct.
Okay.
Right, that's correct.
I understand. Thank you.
Right. Yeah, only works in alkaline.
I have a question to you. So that I want to ask one question about the final topic. The polymer amino group, the endo group can work to correct CO2, but I want to know the influence of the body of polymer, carbon chain part.
Yeah. So what we think is this. All right. We have some evidence that the polymer is buried into the deposit, and only some amino groups are sticking out. So this is so-called, this kind of thing is called the composite electrode, right? So I'm not the first one to electrodeposit a polymer into a metal. Other people have done this too. The reason why we think this is working is the following. We have to be able to stabilize the polymer in the deposit. If we just put the polymer on top of the electrode surface, i.e., make copper and then take some polymer and smear it on, right, like that, it's not stable at all. Polymer goes away immediately, doesn't stick, bye, right? If you use some other kind of covalent chemistry, self-assembled monolayer, thiol on gold, or phosphonate, or something like that, yeah, it sticks a little bit, but then as soon as you go negative, you reduce it off and it goes away. Right, and you can actually collect thiols coming out of your cell. Not so much fun. So this way, we keep the functionality on the electrode surface, and this is actually very stable. This part is quite stable, right? We can keep that there. Nothing's going in solution. No evidence for nitrogen coming out. XPS signals, same, no problem.
Very interesting. How about the structure of the polymer? Is it broken or retained?
Good question. Don't really know, right? We are assuming that it's not broken, but that's an assumption.
Okay. Thank you very much.
Now, I will say the following. If you do a shorter polymer, so this is exactly 100 mer, right? This is what Steve Zimmerman gives me, 100. He says exactly 100. So if you do a shorter polymer, let's say you use a molecule like spermidine cadaverine, if you know those, right? So they're polyamine materials, sort of biological in origin, much smaller, right? Doesn't work.
Okay. The sufficient length of polymer is important to
That's right.
to keep the function of that polymer. Okay, thank you. And other question and comment from audience?
Miho, can I ask a simple question?
Yeah.
Andrew, I noticed that you still get cracking when you use the solvent.
Yes.
Am I right?
Correct.
So you must be interested in shutting down the cracking altogether, I'm assuming, right? Is that what needs to
we
happen?
think the cracking is coming because the particles are, the particles are essentially dissolving into the solvent, right? So you got two ways that you can deal with this. The first way is you can make the pellet even tighter, right? More pressure, more heat, right? Something like that. And the second way is just live with cracking by dissolving the powder straight into the, after ball milling, straight into the solvent.
I see.
And so we've decided to go with that rather than trying to tamp down cracks. In any event, pellets are very unhappy. And if you thought, for example, you were going to use a pellet for a real battery, how are you planning to make those pellets? What's your plan? You're going to have powder. The powder is going to go into some roller, right? It's going to make a perfect pellet. This is going to be very difficult. You know it's going to crack. And this way we can have a liquid material. It's like toothpaste. It's viscous. But you have a liquid material. You can come up there, put it into the cell, slap the cell together. It's easy.
Interesting.
And we all like easy, right? My students really like easy.
Yeah. If you embed any other second phase particles, just distribute them around. Sometimes when cracks approach these types of particles, you can have them such that they can transform and they can shut down the propagation of these cracks. In other words, this is a kind of a micromechanical remedy to solve the process. Once one crack starts, then you have a mechanism there, an internal mechanism that shuts it down.
Yeah.
This approach has been used in composite materials in general.
But then you would have to deal with their lithium-ion conductivity and their stability.
Yeah, that's right. You need,
and that could be more problematic. So this way you get to have your cake, you have your solid electrolyte, right?
Yeah.
But it can't approach the lithium because the solvate's protecting it, dropping the potential, and the solid electrolyte doesn't go and get destroyed by these very negative potentials at the lithium metal.
Very nice, very nice. Yeah. Thank you.
Mr. Son-san, could you?
Is it okay?
Yeah.
So my name is Song at Kyushu University. I have a question about the copper alloy for CO2 electrolyte reduction. So it was very interesting that the cuprous oxide is have an important role for the activity. So as far as I know, that there are so many various factors affecting the CO2 electrolyte reduction, like a subsurface oxide of copper is also one factors to the Situ production. So in your case, you have monitored the cuprous oxide by Raman spectroscopy, right?
Right.
So is there any evidence to say that the cuprous oxide is clearly formed during the CO2 reduction?
Yeah, you can see the growth of the peak. Right, this is the evidence, right? This peak growing in right here. This only comes in when you are doing CO2 reduction. If you have no CO2, this is the oxide peak right here. Why do you see number 2? This is the Raman allowed one, so it's the most intense, right? But without, go back, nothing happens. This is the intensity of that peak. You see it goes down. It doesn't go up, it goes down. So clear difference between no CO2 in this case and with CO2 in this case.
Okay, so only does you mean that only a Raman spectroscopy can be evidence to say that cuprous oxide?
So here you got a problem, right? So what are you going to do? You could do this with an X-ray measurement, assuming there was enough oxide there, right? So glancing incident, surface X-ray scattering, one of those things. You could do that. There is some evidence for that. You can't use IR because this is a low energy region, right? So 500 wave numbers can't do that with IR, right? And everything else is going to be ex situ. So what's her name? Beatrice Coyne in Germany, for example, has done beautiful ex situ work. She pulls it out, sees the presence of these oxides in microscopy and in photo emission work, but that's ex situ. So as soon as you go ex situ, right, you can start saying, oh, excuse me, you know, how much oxygen did you get? What oxygen do you have inside your microscope? Blah, 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 right? This way, we're doing it in operando, under flow conditions.
Okay. Okay.
So Raman is really the way to go in this case.
Okay. Thank you. I understand.
The question, comment there? Okay, no question. So, we can enjoy your talk about the novel phenomena in electrochemistry very, very much. And finally, I'd like to thank Professor Andrew Gebos by cropping. And we are, I'd like to talk here in Eisner. Yeah, please visit Eisner after the coronavirus issue. Thank you for giving a very, very nice talk to us.
You are welcome. Thank you so much.
Thank you very much.
Miho, Andrew and I will travel to Kyushu as soon as the international travel opens up. So we will travel together.
Very good news.
I am looking forward to Hakata style. Right.
That's right.
But do you need to stay for a week, for a few weeks after you entered Japan?
So I think we all want to make sure that everything works okay with quarantine and Delta and things like that, and maybe some more time to wait.
Okay.
This is the problem right now.
Okay.
Right. No one wants to go to Japan and then spend 2 weeks in a hotel room, just like you do not want to come to the United States and spend 2 weeks in a hotel room, right? So not fun.
Right.
But I hope that our circumstance is getting better and better.
Yes. Yes.
Yeah.
And then once, I think, hopefully in spring, right?
Yeah.
I am waiting for, honestly, I thought I wait for an international conference to work, right? Some conference, ACS, ECS, ISE, something please, right? Pacific Chem. So far, no. Right?
Exactly. Yes, and
No possibility. So now I'm feeling like, okay, maybe me as individual, but you know, I've only been in the last 18 months, I've only been in the United States, no Canada, no Europe, no Japan, no South America, just United States, right? So that's, I mean, look at Petros, right? Only United States, right? Very bad.
Yeah, my biological clock has been distorted. I'm not traveling to Fukuoka, so something is strange. You see, in my biological clock, I wake up at night. I say now I'm in Fukuoka, but I'm not. I'm here in Champaign, Urbana. Yeah, definitely. Let's hope that in spring the virus, the pandemic, will be tamed. I'm assuming in Japan, I'm assuming the vaccination will go 80%, right? I'm assuming it will go higher than everybody else in the world. So it'll be easier.
Yeah, recently the number of the people or getting coronavirus is very decreased to less than 100 in
Oh, that's good.
in Tokyo. Yeah.
Oh, that's good.
Yeah.
And I'm assuming in Fukuoka must be less, right? Am I correct?
Yes. Less than 20.
20,
That's very
30,
good.
Less
something like that.
Yeah, that's very good.
Now we are very
Yeah.
safely. We can do everything very safely.
So that's the hope. Soon. I hope soon.
Yeah.
Right.
I believe. So I will close this session. Okay.
Okay.
Hey,
Mm.
Miho,
Thank you very much.
Yeah.
Thank you very much.
Thank you
And
very
Andrew,
much.
thank you.
It is my pleasure. Thank you guys for listening.
Yeah.
Thank you very much.
Okay.
Very much. Bye bye.
Okay.
Good
Bye-bye.
morning.
Good evening and good night.
Thank you.
Bye-bye.
Bye bye. Thank you very
Bye.
much.